All right, Turbo Protocol. I'm Aaron Greenblatt from Turbo. We're building parallelized execution for Geth, and this enables Geth-based blockchains to have the benefits of parallel execution and high throughput. So let's get started. All right, so as we look at the parallel EVM space, there's really three barriers when you try to make Ethereum run in parallel. The first one, of course, is that Ethereum is designed for sequential execution, and also how data is stored in Ethereum using Merkle tries. And the Merkle tries lead to a lot of random I/O, which I think I just heard Keone talking about. So let's talk about these in a bit more detail. I want you to think about each transaction on Ethereum. I want you to think about it as a state transition function. So you have a state of the chain before the transaction and a new state afterwards. And to get there, the transaction executes some code. Now, the minute you run transactions in parallel, the question is, okay, so now I have two new versions of the world because I have two transactions executing at the same time. And this is a classic database concurrency problem, and there's been many years of research and very good approaches on how to deal with this. So the thing about Ethereum, though, is that we store data not in a standard format that you'd have in a database, but instead we have a Merkle trie. And you can see here in the picture, you have the data blocks on the bottom, and then you're hashing up to the top of the tree. Now, ultimately, you still have to store this in the computer somehow, and people use key value stores for this. So for example, LevelDB is a key value store. Typically, the keys are the hashes of the data, and the values are the blocks that you have down at the bottom. So if you think about a sequential read down your data from L1 to L2 to L3, if this were just an array, then this would be very efficient coming from disk. You'd pull 4 kilobyte pages off your SSD, and things would move along quite nicely. But because this is in a key value database, you're actually now doing random lookups through these hashes, and it's tremendously inefficient. And so this is the key scaling issue when you try to parallelize execution on Ethereum. This leads to a parallel EVM design space that really is about state storage. And the first option you have is just to replace the Merkle trie, build your own database. And Keone was just talking about his efforts to do this. And I think it's a solid engineering approach that Monad is taking, but the cost of it is you're not Ethereum anymore. And so you've lost that TVL that's locked up in all of the Ethereum validators. So this is a valid approach. Solana's done it. I think Monad can do it too. But if you want to stay within the Ethereum ecosystem, then you need to do something different. So the next set of approaches is doing some sort of optimizations around Merkle tries. And internally, we've got a name for this. We call it MMF, okay? So Magic Memory Fairy. It's like the Tooth Fairy, okay? So, you get all of the benefits that you could ever name. And unfortunately, when you start looking at these approaches, usually you get to data has to move like faster than the speed of light to meet a latency requirement, or maybe you're violating Brewer's cap theorem of database design. And so these approaches don't work. They make great VC funding stories, but they just don't work. And so your last approach is to do what we do when we have a random access problem, which is we move data into RAM. It's called random access memory for a reason. So every large-scale production system that has these types of problems, every single one of them uses an in-memory database. And within the world of database design, you always scale up before you scale out. And again, it's because of latency. And so the delay between components in the system is a real problem. So if you look at Hazelcast, they run Apple's App Store. It's a big in-memory database. And their scale-out version, it's free because they know it doesn't matter. Their scale-up version, which is what everybody deploys, that's how they make their money. That's what they charge for. And so at Turbo, we're scaling up and then scaling out. Now, of course, this is blockchain, so what we do is we use cryptography to provide the benefits of decentralized ownership, sovereignty, and governance. We provide those benefits using a layer of cryptography, not using a particular network architecture. So I want to talk about software maturity for a bit. Some of you may remember this from the 1990s. This was pretty much any time you went to use your computer after a new version of Windows came out, this is what happened. And your computer would crash and you'd debug, and it was always an adventure. That's why we're using Geth. Geth is the only Ethereum client that's tested, that's mature, that has a solid set of unit tests. And if you're building on any of these new clients, again, intellectually they're very interesting, but it's going to take time before they're production ready. And so we're the only parallel EVM that builds on infrastructure that already exists. And I don't mean to harp on this, but there are huge, huge benefits because we can use the Ethereum Foundation's unit test suite that's built into Geth. You don't have to trust our test suite. You can trust the Ethereum Foundation. It's roll-up stack and modular compatible right out of the box. So you can think of this as a faster version of OP stack. And it's going to be compatible with future EIPs. We get to use all the research that the EF is doing. And especially as Verkle trees come out, state storage gets to be a lot better and will be fully compatible with that. Now, I'm also super excited to say, because of this approach building on Geth, we actually have it working. It's live. And so this isn't some story about a future product. We're actually running the thing. So let me show you a demo, and then this will be coming to RASes very soon. Today, I'm going to show you a demonstration of Turbo Protocol. Turbo is the world's first Geth-based parallel EVM. On my screen, I have 3 windows. The top window is running htop, so it'll show you the status of the CPU cores. In this case, they're on my laptop, which is a MacBook. In the middle window, we'll be executing code, adding transactions to a chain, causing the chain to then execute the transactions. And then the bottom window is a standard Python shell. We'll be using that to compute some performance metrics as we go through the demo. First, let's get a new chain started. So we type in start into our demo script, and that creates a new Genesis block and then adds some transactions to the chain. Next, we can add additional transactions to the chain, and these are basic token swaps, so you can expect fairly high performance as we go through the rest of the demo. So first, we'll try adding 10 blocks to the chain with 10 transactions each. Now you can see we've added those blocks to the chain, and for each block there's an elapsed time to add it to the chain. And you'll notice that that time actually varies quite a bit. We have very small blocks here. Now what's going on is that this computational workload is scheduled like any other computational workload on a computer, so this is not real-time scheduling. There are no latency guarantees, and in Linux you have a real-time kernel when you do have specific latency requirements. So for example, when you're processing real-time digital audio, blockchains process transactions in blocks specifically so there isn't this latency requirement. There are folks in the industry who have recently been talking about real-time blockchains. They're just talking about sequencer pre-confirmations. Ultimately, sequencer pre-confirmations are a different area of research from parallel EVMs. So all of the parallel EVMs will use sequencer pre-confirmations, but parallel EVM is fundamentally about computational execution, and the pre-confirmations are a complementary technique that you can use to improve responsiveness. Back to our demo and back to performance numbers, what I'll do is I'll just select the bottommost execution time and use that to compute TPS in the bottom window. So we have 10 transactions divided by 1.2 milliseconds. It gets you about 8,000 TPS on very small blocks. Now, as you increase block size, you'd expect performance to go up because that's the whole reason we're batching these things into blocks in the first place. And sure enough, it does. So when I add 50 transactions per block, like in this case, now we get closer to 18,000 transactions per second. And I can keep this going. So now I'll have 1,000 transactions per block. And remember, these are fairly simple transactions, so that's actually a very reasonable number.
And now you're looking at 59,000 transactions per second. We experimented with this a bit more, and our laptop seems to top out at about 400,000 transactions per second. In this case, you can see we did 419. So this is on a MacBook laptop without any special software or hardware customizations. It's an off-the-shelf computer. Now, practically speaking, if you look at blockchains today, and especially roll-up stacks, you get about 500 usable transactions per second. So 400,000 is a major, major improvement. It unlocks all sorts of applications that you couldn't build before. There are several groups that are saying you have to move away from Geth to get this type of performance, but we already have this performance using Geth on commodity hardware. Lastly, I also want to show you that when we add transactions, all of the cores actually do work. And so you are really getting that parallelization effect. You can see that here. Now you'll also notice that the cores aren't necessarily at 100%. And part of that is because we're running fairly memory-intensive transactions. When you're doing token swaps, that's very heavy on state access. And so if you were to add more computation to each transaction, you would expect the CPU cores then to go to 100% because they're limited by compute and not by memory. That's today's demo.
Thank you. So just to recap here, we're Turbo Protocol. We're a parallel stack secured by Ethereum. We're getting 400,000 TPS today on a laptop, and we're built on Geth for interoperability and for reliability from day one. I'm here today. Our head of ecosystem, Barry, is in the back of the room at the camera today. We'd love to get in touch with you. We're hiring. We're onboarding launch partners. Barry's Telegram is up here. The other QR code goes to our website, and we hope you enjoy the rest of the conference.